All right, today we're diving into bee trees and their super popular cousin, the bee plus tree. This is the data structure that's quietly powering pretty much every database and file system you've ever used. It's the silent workhorse that makes finding your data so incredibly fast. So, to really get why these trees are such a big deal, we've got to start with the problem they were born to solve: the disk access problem. It's a huge challenge of scale and speed that really defined a lot of modern computing. Just imagine for a second you're a database. You need to find one single piece of information, let's say one customer's order, out of a billion of them. But all that data isn't in your superfast memory. It's sitting on a much slower hard drive. How in the world do you find it without just reading everything? You see, the real problem here isn't just the search itself. It's all about minimizing how many times we have to go and read from that slow disk. Every single read is a massive performance killer. So the goal for our data structure is really simple: find what we need with the absolute fewest disk reads possible. So how do we crack this nut? Well, let's use a really great analogy to get our heads around it. Forget about computers for a minute and just think about a massive library. Instead of running down every single aisle, you start at a high-level index. Think of it like a top shelf that just has big labels like A through F or G through M. In the world of trees, these are called internal nodes. They don't have the actual books, just directions on where you should go next. Each of those labels points you to a more specific section on the shelf below. So if you're looking for a book on data structures, you follow the A to F sign, then maybe a C to D sign on the next shelf down, and so on. You're efficiently getting routed through this huge collection. And right there, that's the absolute key to the B plus tree's design. The actual data, the books, they only live on the very bottom layer. In our tree, these bottom shelves are called the leaf nodes, and they're all perfectly sorted in order. So what we've been calling our bookshelf is formally a B plus tree. And that little detail about the leaves being linked together like a chain, that's its superpower. It means once you find one book, you can just scan over to the next one super easily, which is amazing for queries like find all the orders from last week. Okay, that's great for a static library, but what happens when we start adding more books? How does this whole thing stay so perfectly organized when one of those shelves gets too full? Well, when a shelf gets packed, the system doesn't just try to cram more in. Nope, it does this really elegant three-step split. The shelf splits into two, and then a new label, a separator, gets sent up to the shelf above it to direct traffic between these two new shelves. And this is so important to get. The tree actually grows up, not down. When that very top shelf, the root, finally splits, a brand new top shelf is created above it. That's the secret sauce to keeping the whole structure perfectly balanced, and most importantly, incredibly short. All right, now we get to the real magic, the math that makes this whole thing ridiculously fast for databases. It all comes down to how wide our bookshelf is, not just how tall. You see, unlike a simple binary tree where a node can only have two kids, a B tree node can have hundreds, maybe even thousands of children. This is called high fan-out. In our library, that's like each guide shelf having a huge number of labels. It lets us make a much better decision at each step, which massively cuts down on the number of shelves we have to visit. And what does all that high fan-out get us? It gets us this: 4. Just 4. That's it. That is the typical number of times you have to read from the disk, the number of jumps between shelves, to find any single record you're looking for out of millions or even billions of other records. It's wild. And here's the math that makes it all happen. Yeah, O log Bn might look a little scary, but the secret ingredient is that little letter B at the bottom. That's our massive fan-out. Because that base B is so huge, the final result of the equation, which is basically the height of the tree, ends up being teeny tiny. It's how you turn a billion records into just 4 steps. So, where does the B plus tree fit in with other data structures? Well, look at this. A hash index? Sure, it's technically faster if you know exactly the one item you're looking for. But try asking it for all sales from last week, and it just falls apart because there's no order. B plus trees, they are the undisputed champions for data on disk, excelling at both finding specific items and scanning through ranges. So after all this, why should you care? Where does this stuff actually show up in the real world? The answer is, well, it's pretty much everywhere. Seriously, from the second your computer boots up and has to read the file system, to every single time you search for something on a website, you are interacting with B+ trees. They are the indexing bedrock of almost all the software we rely on every single day. So the big takeaway here is that this isn't just some dusty, abstract theory from a textbook. No way. This is the real-world, battle-tested engine that's quietly and efficiently organizing almost all of our massive stores of data all the time. And that brings us to one last big question to chew on. The B+ tree was designed for a world of slow spinning disks. But today, we've got mountains of RAM and SSDs that are lightning fast. So is this incredible bookshelf that we've built still the right one for the data of tomorrow?